This is lesson 2.2 of our Precalc 12 class. Unit 2 is called Polynomial Functions. Lesson 2 is called Characteristics of Polynomial Functions 2. In this lesson, we're going to talk about a few more words to describe polynomial functions, that being end behavior and intercepts. When we talk about end behavior of the function, we talk about what happens to y as x goes all the way to the left or to the right. And we have notation for that. So when we say to the right, we're saying as x approaches infinity. When we say all the way to the left, we're saying as x approaches negative infinity. So x goes left and right, so y goes up and down. So if we were to say y goes to negative infinity, we're saying down. If we say y goes to infinity, we're going up. So x values are left and right, y values are up and down, so that hopefully makes sense. A couple examples: if I have a graph that starts high and ends high, then we say as we go left, we go up. So as x approaches negative infinity, y approaches positive infinity. And as we go to the right, the curve also goes up. So as the curve goes right, or as x approaches positive infinity, things blocking the way, there we go. As x approaches the right, as we go to infinity, we go up. Y approaches positive infinity. In the second example, as we go left, we go down. So as we go left, as x approaches negative infinity, we go down. Y approaches negative infinity. And as we go to the right, as x approaches positive infinity, this graph goes up. Y approaches positive infinity. On the second graph, the third and final graph, the end behaviors both go down. So as we go left, x approaches negative infinity, we go down, y approaches negative infinity. And to the right, as we go, x approaches positive infinity, we also go down, y approaches negative infinity. And so hopefully that makes sense, and hopefully the notation also makes sense. Right. Okay, so if I were to look at just the polynomial function expression and not a graph, we can get the same information. We need to know two things. We need to know the degree, if it's odd or even, and we need to know the leading coefficient, so that number on that leading term. So for example, A, here's the leading term. The degree is 3, and the leading coefficient is 8. So the degree is odd, and the leading coefficient is positive. So here's our cheat sheet right here. Every odd degree polynomial with a positive leading coefficient is going to have this approach. As in, as you go left, it goes down, and as you go right, it goes up. And if you think about it, hopefully that makes sense. Try a few examples. Y equals x. X is a degree of 1, that's odd, and it's a positive leading coefficient of 1. X to the power of 3 starts low, ends high. X to the power of 5, x to the power of 7. If we were to do so that would be that one right there. So because it's an odd degree and a positive leading coefficient, we know this is a situation. As we go left, we go down. As we go right, we go up. Or as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. So if we were to have an even degree function with a positive coefficient, both end behaviors are going up. If we made that a negative coefficient, I would flip both of them to be going down. So even degree negative coefficient, the y values are all both approaching negative infinity. And then for odd, if you were to make it a negative coefficient, but be an odd degree, starting low and ending high would be reversed. So it would start high and end low. And you could graph some examples. Do those same odd degree functions, x to the power of 3, x to the power of 5, but make it negative x to the power of 3, negative x to the power of 5. And you'll see that you get that relationship for that end behavior. Example B was quite boring, we decided, because it's also an odd degree polynomial with a positive coefficient. And that would be the same as example A. So the question was, how would you change example B to make it an even degree polynomial with a negative coefficient? And we said we could change the 3 to a 4, and we could change the 5 to a negative 5, and that would work. So if this was example B, negative 5x to the power of 4, it'd be an even degree polynomial with a negative leading coefficient. And that would mean that the end behavior, as we go left, we go down, whereas x approaches negative infinity, y approaches negative infinity. And as we go right, we go up, whereas x approaches positive infinity, y approaches negative infinity. All right, that's end behavior. Now let's talk about intercepts. We mentioned before in the last lesson that y-intercepts are the constant term. And so a little more on that. When I look at a y-intercept on any graph, the x value is always 0. So when we look at a function notation, the y-intercept is the same thing as f of 0, because x would be 0, and whatever the output is the y-intercept. So we can evaluate a y-intercept by calculating f of 0. In this case, example A, it's a standard form, so it's really easy to see the constant term. The constant term is the term without any x values. And so it's really easy to see that's going to be the y-intercept. If we try to connect that with f of 0, when I plug in 0 for all the x's, all the terms with an x in it are going to be multiplied by 0 and wash out. The only term not being multiplied by 0 is the constant term. That's why the constant term is the y-intercept, when we think about it from function notation at least. Example B, we can find g of 0, and that would be the y-intercept. In this case, it's also in standard form, so I can read the constant term really easily. So plus 0 tells me that the y-intercept is 0, but also g of 0 equals 0. That also tells me the y-intercept is 0. In examples C and D, they're not in standard form, so we can't read the constant term. You could multiply and FOIL it all out and find the constant term to find the y-intercept. That would work. But in this case, I think it's easier to just calculate h of 0 and k of 0 and get our y-intercepts. So the y-intercept for C, h of 0 is 0, so the y-intercept is 0, 0. Example D, k of 0 would equal 2, so the y-intercept is 0, 2. Okay, x-intercepts. X-intercepts are anywhere where we cross the x-axis. Any x-intercept would have a y value of 0. So if we think about x-intercepts from function notation, it's whenever f of x equals 0. So y-intercept is evaluating f of 0. X-intercept is finding when f of x equals 0. And this is a more complicated question than just plugging in 0, like y-intercept. Because in this case, we replace f of x with 0, and we solve for all possible solutions. So that means there could be more than one x-intercept. So example A is a polynomial in factored form. Each factor can give us a potential x-intercept. Because again, we're trying to find when this whole thing, f of x, equals 0. And we have 3 factors multiplied together. If any one of those 3 factors is equal to 0, it's an x-intercept. So if x is 0, we have 0 times anything. If x is 4, we have something times 0 times something, because 4 minus 4 is 0. And if we have negative 6, we have something times 0. So 0, 0, 4, 0, and negative 6, 0 are all x-intercepts for f of x. Now example B, there's x squared minus 9 is one factor, and x minus 6 is another factor. X minus 6 tells us that 6, 0 is an x-intercept. But also, x squared minus 9 gives us not 1, but 2 x-intercepts. If you think about it, there are 2 solutions. If I take this factor and set it equal to 0, and I solve algebraically, X could be a positive 3. 3 squared is 9. 9 minus 0 is 0. Sorry, 9 minus 9 is 0. But also X could be negative 3, because negative 3 squared is still positive 9, and 9 minus 9 is still 0. So X squared minus 9, this factor gives us two X-intercepts, 3, 0 and negative 3, 0. If you recognize this as a difference of squares, then you could break this up into X plus 3 and X minus 3, and you get the same two X-intercepts. Example C has a similar setup. We have an X term, we have a difference of squares term. It's going to give us two intercepts, and we have another term that's going to give us our fourth intercept. Example D has two intercepts. This one's got a fraction. In general, the rule of thumb is you can't have more, the number of intercepts you have can be no more than the degree. So for example 1, we have a degree of 3. There can only be 3 intercepts. There can be less than 3 intercepts. There could be 2 or 1 or none. There can't be more than 3. Yeah, so that's that. So far, all of our number of intercepts are equal to the number of degree, but that won't always be the case. Okay, one more thing. X-intercepts are also known as roots or zeros. We use x-intercepts, roots, and zeros somewhat interchangeably. Usually, when we talk about the graph, we talk about roots or intercepts. Usually, when we talk about an equation, we're talking about zeros. But keep in mind, they mean the same thing. Okay, some examples. Find the x-intercepts. There they are. Note that it doesn't have to cross the x-axis to be an x-intercept. Negative 8, 0, the curve touches or kisses the x-intercept or x-axis, but doesn't actually cross it. It's still an x-intercept. So this one has 3 x-intercepts, and so does example B. Alright, so we've learned some more vocab and key terms and words to describe polynomial functions. The end behavior, we have some new notation to describe end behavior. And we have an understanding of how to look at functions to find x and y intercepts. I will say that using function or finding x-intercepts from the function equation is a lot of work, or can be a lot of work. And so we're going to spend some time after this lesson working on our algebra skills in order to solve more complicated polynomial functions to find the x-intercept. But for now, finding from the graph is good enough.